Good morning, everyone. Thanks for coming. So I'm Sasha. I work for a training and consulting company back in Israel called Sela. And I'm really excited to talk about BPF in general. And this talk specifically that also adds some JVM monitoring into the mix should be particularly interesting. If you have Java applications in production, you should know there's a new set of tools and kernel technologies that can be used to monitor them. And even if you don't have Java applications in production, a lot of the tools we'll be looking at today can be used with other languages, with other runtimes as well. So what I want to do is show you some really nice, low-level, production-ready, low-overhead Linux tracing tools that can be used for investigating JVM application performance. And there's four major things I want to show you: which tools can really be used in production with JVM apps, how BPF is a bit different than traditional Linux tracers and traditional Linux performance monitoring tools, especially where it comes to high frequency events that you want to trace. I want to show you some examples of how BPF tools work with JVM apps specifically and what the pitfalls you should be aware of. And finally, I'll show you a bunch of little examples of how to conduct a tiny performance investigation, as many as fits in 45 minutes. So let's start with talking about something that a lot of people aren't aware of, and that's the built-in static trace points in the JVM that we can trace using BPF tools as well as some other tools. These are available in the OpenJDK, not in the Oracle JDK, unfortunately. But let's just take a look at what they are, and maybe then you'll petition Oracle to add them in their release as well. So if you look at the main JVM library, and you use the readelf tool, that's a tool that parses the elf header, and then the -n switch, which I used over here, the -n switch asks for note sections in the elf to be displayed. And you see a list of a bunch of different things with provider and name. And these are trace points embedded into the JVM binary that can be traced at runtime. If you don't use them, there's zero overhead. Nobody even cares they're there. But if you have a tracing tool that's capable of attaching to these things, you can extract interesting information. So you see on the slide, these things include garbage collection events, classes being loaded, object allocations, threads starting and stopping. There's a few dozen trace points like that embedded in the JVM library. And I also have a slightly different way of showing these. In BCC, which I'll talk about shortly, we have a tool called TPList, trace point list, which you can attach to a running process, and it will print all the different static trace points embedded in that thing. And if you look again at a Java process, it has a bunch of these interesting things that can be traced. So again, object allocations, methods being called, lock contention events, classes being loaded, a bunch of interesting things for tracing an application performance. And this can be done at runtime. So the process is running, there's no extra steps we had to take, and these trace points are there waiting for someone to enable them. And to understand the format, the arguments of these trace points, you can still use TPList, or you could also use the readelf approach. The problem is, if you look at the arguments for these trace points, you can only see, as you see here on the slide, the number of arguments and the sizes of each argument, but you don't know what they are. So what is the first argument? What is the second argument, other than being 8 or 4 or whatever byte-sized integers? So this is where you need to go to either the documentation or some embedded documentation that comes with the runtime that you're tracing. For JVM specifically, there is a systemtap probe definition file. And so if you've used systemtap before, this is how systemtap defines the different probes for tracing. And this is where you can find the actual explanation for what the different arguments are. So in this example, for the monitor-weighted probe, this is a probe that gets called, a trace point that gets called when you wait for a lock in a JVM application. You can see the arguments include the thread ID, the class that you are waiting on, so the type of the object that you are using as a lock, and so on. So these are the arguments, and this is how you extract the information about these arguments. So let's see how to actually trace a couple of these things before we talk about BPF in a bit more detail. So in this example, suppose you have this application running, and it's printing undesired stuff to the terminal. You don't understand where it's coming from, and you're interested where it's coming from because it's suggesting there's some kind of error or misconfiguration. So it might look something like this. It's running, and it's just constantly printing these weird errors. And in a large enough application, in a large enough system, you don't always know where this is coming from, and looking at the whole source code, trying to find that error message could be tricky. So here's what we could do. There is a tool in BCC, which we'll talk about in a few minutes, called trace, which can attach to an arbitrary process or run system-wide and print a log message when something interesting happens. And it has this custom format for attaching to things. So it can attach to a bunch of different things. In this example, we will be attaching to a kernel function. But you can also use trace, and I'll show you examples. You can also use trace with JVM tracepoints that I've mentioned. You can use it with user space functions. So let's try to decipher this line. So first of all, it has to run as root. Trace and BPF and all these tools, they do require admin capabilities. And then here's the attached target. This is the thing that we're attaching to. It's a kernel function, syswrite, which implements the write system call. And then we have this filter or condition that has to be met. So the first argument of the write syscall has to be 1. And that first argument is the file descriptor. And file descriptor 1 is usually the standard output. So what we're doing here is we're tracing writes to standard output. And then we have a message to be printed when we get there. And so this is like a printf-style format string. So we're printing a string, %s, and the value we're printing is the second argument of the write system call, which is the buffer that we're writing out to standard output. And then we're asking for a stack trace to be included, a user stack trace with U, or K for kernel stack trace. And finally, we have a process filter. So we're only interested in that Java application. This is completely ad hoc. It doesn't require any code modifications in your Java process, of course. And let's see the output for a moment here. So this is what it looks like. I've highlighted with different colors the pieces that match different parts of the invocation. So you can see the process ID, you can see the Java process name, you can see the function we traced, you can see the message that was being printed, which is recognizable. That's the error message we're interested in. But the stack trace doesn't look quite so good. Specifically, there's a bunch of function names on that stack trace, but there's also a bunch of unknown frames. In fact, all the Java code is unknown, is showing as unknown. And so this happens because trace, as well as a bunch of other tools, they don't know how to translate Java just-in-time compiled symbols, Java just-in-time compiled code addresses into function names. When the code is generated at runtime, as it is with the Java JIT compiler, there's no way for these tools to just magically resolve these addresses back to function names. So you see function names for everything except the Java application that I'm trying to tell you how to trace, which is unfortunate. So the way around this, one of the ways around this, is to ask the JVM to generate information that maps these code addresses to function names. And one tool that does that is called perfmapagent. It's a very nice, neat open source project. And you run it, attach it to a given Java process, and then it generates a file, which the BPF tools I'll be showing you today expect in a certain location, so sort of a coordination between the two different tools. And that file has mappings, like I've told you, between code addresses and function names, code addresses and function names. Once you have that file in place, you can run that previous command again, and now you can resolve the function names on the stack. So this is a complete stack trace of a running Java application, which is writing something suspicious to standard output, and we have just successfully traced it and printed the stack trace, and we found the suspicious code which is responsible for that error message. So you see a bunch of Java JDK functions, but then at the end, highlighted there, you see my actual application code, which is responsible for that printout. Again, completely ad hoc with no code modifications. You basically have a tool that lets you embed these lightweight log messages at runtime in any application, in any process, and this is how it works with the JVM. I want to show you a slightly different example before, again, we talk about BPF somewhat more in a little bit more detail. So in this example, I might have an app running in production which is causing lots of garbage collections. And for Java apps, garbage collection is just a fact of life, but at the very least, you might not want to invoke it yourself. Like if the GC decides it has to run, well, that's one thing. But if the app is just constantly invoking the garbage collector manually, that's something that needs to be investigated. So in this example, we will have a Java app that's causing lots of garbage collections by causing system GC directly, and we want to figure out where it's happening. Again, in a large code base, could be tricky figuring out where that event is coming from. So first, here's what the symptoms look like. If I run this Java app with print GC, with the print GC option, it prints out a line whenever there is a garbage collection. And the highlighted part, system GC, that's the reason for that GC. So system GC is a garbage collection that was forced by the application as opposed to the usual heuristics the JVM would apply. And if you look at the numbers for the details on that GC, it's not really cleaning up a lot of memory, and we are very far from the maximum heap size. If you're used to reading log messages from the GC, it really looks like useless garbage collections are happening, just wasting lots of CPU cycles. So here's what we can do. Another magic incantation, invoking trace again, but this time we'll be tracing a slightly different event. This time I'm interested in an actual Java function in system GC. That's the thing I want to trace. So let's see. The attached target, the thing we are now attaching to, is a trace point in the JVM called method entry. And that's actually something that wouldn't be enabled by default. You need to add a command line flag to turn this static trace point on, because it has a certain overhead. You will now be able to trace every single method invocation in the JVM, so that's going to be a bit expensive. But once you've done that, I'm attaching to that method entry trace point, and my filter this time is that the fourth argument of that trace point is the string GC. And again, if you go back to the trace point definitions I was showing you in the beginning, you'll find that the fourth argument is the method name. So this is basically looking for all the method invocation where the method name is GC. It's not enough. I should have also looked at the class name, because I could call one of my methods GC, and then it would also trace them. But it's good enough for this demonstration. The message we want to print is just there was a forced induced garbage collection. We want the stack trace, and we want this to be looking at just one individual Java process. And here's what the result looks like. We get the stack trace for that GC event, which tells us where this induced garbage collection was coming from in the Java process. So this is just a piece of code in data fetcher fetch data, which is manually calling system GC and causing lots of garbage collections. So that's a couple of examples of using trace. This is just one tool based on this BPF kernel technology that we'll be talking about. So let's move on and see what it is. How many of you have heard of perf or used perf before? OK, so quite a few. And it seems like if you look at the last couple of years at Java conferences, there's always a talk on using perf for profiling JVM applications, for tracing various events in JVM applications, and generating flame graphs is also quite popular. So just for example, this is not a talk about perf, but you could, for example, run a recording using perf, and that records CPU samples of what the process is doing over time. And then you could take the results from that perf run and post-process them in user space and create, for example, a flame graph, create a visualization of the hottest stacks in that Java application. This is lovely and works, and again, there's been a lot of effort gone into improving this workflow of using perf with Java applications. So what's wrong with that? Like, why am I telling you about some other technology which is not related to perf at all? So the main thing that's wrong with perf, for our purposes here, is that the workflow of using perf usually relies on pushing lots of data to a file for post-processing in user space. You can't process the results as they occur right at the source. You have to buffer them somewhere, usually in a file, and then run a bunch of tools that would post-process that information and generate some kind of visualization, flame graph, histogram, whatever you're interested in. Just as an example, I tried to do a perf recording where I recorded every single packet receive event, not the packets themselves, not like TCP dump, just the event a packet was received while I was downloading a file at a 1 gigabit per second connection. And I got 19 megabytes of data per second recorded as part of my trace, as part of my perf recording. This is an unsustainable rate. If you record like that for just a few minutes, you won't be able to analyze the recording anymore, or you will run out of disk space, like whatever happens first. And it's definitely unsustainable in production, again, for high-frequency events like this. This is a major, major problem with perf. And even though there's some ways around it, the key here is we can't do any sophisticated processing at the source where the events actually occur. We have to record a lot of stuff we don't need and then discard it later in user space using some other processing tool or a script. And this is where BPF comes in. So BPF was invented originally in the early 90s. And BPF stands for Berkeley Packet Filters. Probably a lot of you have heard this abbreviation before. And indeed, it was originally used for filtering packets. So you could run something like Wireshark or TCP dump even today, and they would use BPF to represent a packet filter for the things you want to record, for example, packets to record or packets to discard. So BPF takes a human-readable rule, like the ones you use with TCP dump or Wireshark, and converts them to an underlying representation, to an instruction set that originally would be interpreted in the kernel. So you convert the human-readable rule to BPF instructions, and that is then interpreted in the kernel for each incoming packet. So it's kind of like JVM bytecode, right? We compile Java code to bytecode, and that gets interpreted or JIT compiled. So same thing happened with BPF over the years. Originally, it was an interpreter that would interpret each single bytecode instruction, each single BPF instruction. Today, BPF has a JIT compiler. So the BPF program you provide can actually be compiled to the underlying architecture, like x86 or ARM. And BPF today has a lot more usages than just packet filters. And this is why we're talking about BPF when it relates to JVM performance monitoring, which is like the farthest away you could be from packet filters. So let's see how BPF works in this tracing scenario. So you have in the kernel a BPF runtime, which has been available for a while, but now it can apply to a lot more scenarios. And in user space, you have some kind of control program, a tracing program, a script. So what happens first is that your user space application installs a BPF program into the kernel. So it basically loads a bunch of BPF instructions into the kernel, and it attaches them to the events you would like to trace. So you can now use BPF programs to trace interesting performance-related events. And that includes JVM trace points, like garbage collections and method invocations, but it also includes a bunch of kernel stuff, such as system calls, kernel trace points for I/O and file system access and networking, and a lot of events, millions of events if you consider that every function in the kernel and every function in user space can generate events and invoke a BPF program. So when an event occurs, and the event could be coming from a user space application or from the kernel, your BPF program would get invoked. And then your BPF program, if it was just a packet filter, it would be a completely stateless thing. It would just say, record this packet or drop this packet, something like that. But for performance tracing purposes, BPF programs can be stateful. So they can record information. They can aggregate information. So there's two major ways to do that. One way is using maps. So the BPF program can store information in a key value store, in a hash table. So for example, you could count events. You can generate histograms. You can find the maximum, minimum, and average values for a set of events. So your BPF program can do aggregations in real time. It doesn't have to record everything to a file, like perf does. Or the other option is your BPF program can write binary data into a buffer, which is shared with user space, and then user space would just read that buffer and process the events like perf would do. But you do have the option of doing processing in the kernel. And then what happens is your user space application can be invoked with data from that shared buffer, or your user space application can go ahead and read and update that shared hash table. So you basically install this tiny little safe program that runs in the kernel, attaches to interesting events, processes them really, really fast, and doesn't necessarily generate a lot of data as it is processing. So you don't have to write anything to files, for example. You can do the entire processing in memory and discard events immediately as you don't need them anymore. Now, the only reason why BPF hasn't yet replaced every single performance tool based on older technologies is that BPF is only available in relatively recent Linux kernels. So again, BPF for packet filters has been around since the 90s. BPF for performance tracing, for attaching to different performance-related events, that's only been available in the 4-point-something kernel series. Just as an example, tracepoint support, which is necessary for tracing kernel events like disk accesses, is only available in 4.7. Some other things like stack traces are only available in 4.6. So my examples where I printed out a stack trace of the JVM process, that would only work on kernel 4.6. There's some ways around some of these limitations, but if you have a kernel that's older than 4.3, let's say, you won't be able to use some of the BPF features we talk about today. And that's obviously changing as people are updating to newer kernels, but it's something to be aware of. Alrighty, so just to summarize, the main difference between the old way and the new way, the perf-based way and the BPF-based way, is just this one tiny thing. With the perf approach, the key strategy is that you generate lots and lots of data to a file, you generate lots and lots of events into a file, and then you process them in user space to generate maybe something like a histogram, which is not really a lot of data. With BPF, the generation of the histogram happens in the kernel, at the source, and the only thing that actually is shared with user space is the histogram, which is, what, 100 bytes maybe. So instead of generating lots and lots of data only to discard 99.99% of it, you discard it at the source. So that's why BPF-based tracing tools can be a lot more efficient and faster than traditional tools. So let's see a few examples of using some tools based on BPF. The front end we'll use, which contains a lot of tools based on this BPF kernel technology, is called BCC. It stands for BPF Compiler Collection. And so you might say it's a collection of compilers, but it's really also a collection of tools. There's lots and lots of tools developed by engineers from various companies for tracing various aspects of Linux and the JVM as well. This is a diagram of some of the performance-related tools we have in BCC today. I've updated it not long ago, but there's been some new tools added since, I think. And if you look specifically at the JVM part, there's 6 tools that work with higher-level languages, with higher-level runtimes, and they work with JVM applications as well. For example, we have tools for tracing garbage collections. We have tools for tracing method calls. And these are things working on higher-level languages. If you go a little bit lower into the kernel, we have tools for tracing TCP events. We have tools for file system events. And we also have a collection of these cross-cutting general-purpose tools like trace that I was showing you, which work with anything, which work with any performance data source on the system. So let's see some examples. This is just a checklist of some of the useful tools I'll be showing you today. There's a lot more, so let's just get started with some scenarios. The first thing I want to show you is what perf would be traditionally used for, and that's identifying CPU bottlenecks. So you have this JVM application. It's taking lots of CPU. You want to figure out where the CPU is going, what hot methods are running. So this is what it looks like in top. You have the Java process taking almost 100% of a CPU. You want to investigate. So first, and that's not entirely related, but just to show off one of the tools, we have a tool in BCC called uthreads, which I've ran here. and it prints a message whenever a thread is created or destroyed in a Java process. And it even gives you the thread name that's being created or destroyed. Just an example of a tool that really understands the language, the runtime-specific trace points, and uses them to augment the output with some useful information like the Java thread name. So anyway, we have lots of these thread creation and destruction events, just something to remember in the background. So now we run a tool called Profile. And this is a tool that traces samples the CPU while that Java application is running, and aggregates in the kernel the call stacks of what the application was doing. So it doesn't write out a huge file that has millions of CPU samples. It aggregates these events in the kernel to figure out which call stacks in the Java application are responsible for lots of CPU usage. Again, the aggregation happens on the kernel side. Now, the output, if you just run it in a terminal, would look something like this. It prints out a stack. So this is a stack trace of my application. And then a number on the bottom which says how many times this call stack was seen. So this specific call stack was seen 43 times. And so you could look at what the hottest stacks were and go back to your source code and maybe fix them. You could also take the whole thing and convert it into a flame graph. So in this example, I've ran Profile with an additional flag called -f, which stands for folded. So the output would be already suitable for generating a flame graph. So again, the only thing we get out of the kernel is the folded stacks information. We're not pushing every single event for analysis in user space. And then the result could be a flame graph. This is a pretty boring flame graph, but it does show that in addition to the Java process, we also see other processes. Because in this case, I've done the profiling system-wide. So other workloads taking CPU time also show up. Like I've had a DD process running and DNF installing some package. And I've ran strace just to generate some CPU stress. And among them was my Java application. And you can see the stack in the Java application responsible for lots of CPU usage. If you haven't used flame graphs before, we don't have time to explore them in detail right now, but they're extremely useful for visualizing this kind of thing, for visualizing lots and lots of stack traces. And some other things I'll show you later also use a lot of stack traces and could benefit from flame graphs. So this is just CPU profiling of a Java process with a lightweight BPF-based tools. Nothing is written to files at any point except the end result, except just the folded stack traces where most of my CPU time was spent. Now, another concern I might have about this particular application, by looking at the source code, maybe I identified that there is a lot of synchronization going on. Like this is an application that computes prime numbers, and in the source code there's actually a lock. So whenever I find the prime number, I acquire a lock, and then I insert that prime number into a shared data structure. And this is running across multiple threads. So I might be a bit concerned that the locking, the synchronization, is an issue. This is the sort of thing that maybe you even want to do in development, not actually just in production. So to figure out if we do have a bottleneck around synchronization, we can use the JVM specific probes. The JVM trace points, there is a trace point for entering a lock and for waiting on a lock. So whenever you have a thread that waits on a lock, we can get an event out of that. And we have a tool in BCC called argdist. And this is a tool that would attach to something, attach to some kind of event. For example, the monitor contention event that we're using in this case, monitor contended enter. So we tried to acquire a lock, and the lock was taken, so we had to wait. And what argdist does in this case, it's just very simple. It counts the number of times it happened over an interval. So it prints a message every 5 seconds, and it says how many times did that event occur. So the first printout you see here doesn't even have any output. So it didn't really happen. The second output you see here had 3 contentions. Then nothing again, and nothing, and finally on the very bottom there were 9. So I'm only having like single-digit number of lock contentions in 5-second intervals. So hopefully the locks are not really a serious problem for this application. So that's just another example of applying the trace points in the JVM that we were talking about, like the monitor contention trace point, to the BPF tools, which don't require recording every single event or adding logging statements to your application, just aggregating this data in the kernel. So let's see another slightly more sophisticated scenario. In this example, I have a Java application running and talking to a MySQL database. And I have some slow queries once in a while. So just by inspecting the HTTP requests even to my application, I can see that some requests are slower, and I think I've pinned it down to SQL queries taking longer than expected. So first of all, to even diagnose SQL query performance, we have a tool in BCC called dbstat. And that's a tool that currently works with MySQL and Postgres, but in theory, it could be expanded to any database that either has trace points for starting and finishing a query, or maybe even just use dynamic instrumentation to figure out which function in the database engine is responsible for query execution, and just trace that. So basically, even though my example here is using MySQL, you could extend this tool to other databases as well. So in this case, I'm running dbstat on the MySQL database, and it tells me the following. This is a histogram of query execution times. So 3,027 queries took less than a millisecond to complete, 0 to 1 milliseconds. And this is why the histogram doesn't really look like a histogram. It looks like just one single bar that takes all the horizontal space. But if you look at the bottom, there are some outliers. There were 8 queries that took between 1 and 2 seconds. So this confirms my suspicion that we have some really slow queries happening here. We could also ask dbstat to just print the slow ones in the first place, to ignore anything that was faster than a certain threshold, and that shifts the shape of the histogram. So that's nice, but now what is the database doing? So maybe it's overloaded or something. Looking at CPU utilization for the database, I see 2% CPU consistently. So I want to figure out, again, which queries are running and what's happening there. So we have another tool in BCC called dbslower, which is the same thing as dbstat, except it also prints the query text. It tells you what the query was that was slow. And this is now more interesting. I could tell dbslower to take only queries slower than 500 milliseconds and print them. So you see 4 queries printed on the screen, and there's more if I keep running. And it's always more or less the same time. So these are queries taking roughly 2 seconds. And it's always the same query. It's actually a function, a database function, a procedure called getProduct. And the argument was always 97. So that's really suspicious here. Unfortunately, dbslower only prints the procedure invocation. But I suppose inside that procedure, there could be maybe dozens of additional things, like additional internal queries and procedure calls, which we're not seeing here. But the database has more detailed trace points available. Specifically, MySQL has a query exec start trace point available. And I'm using the same trace tool that we've already seen a few times to trace that trace point in the database engine. And that prints also queries executed by that procedure internally. And that looks as follows. And then you see that usually the getProducts call is quite fast, and it runs some internal queries as well. But here, when invoked with the argument 97, it looks like it would then go and sleep for 2 seconds. And that hopefully explains the degradation. So this is tracing everything that the database is executing, every single command, every single statement. Now this is fun, but I also wanted to see where is this coming from on the Java side. This has been all MySQL tracing, but where is this coming from on the Java side? Like which part of my code is calling that slow query in the first place, and which part of my code is responsible for that argument 97, which could be the problem in itself. So this is not something we have a ready-made tool for, but I've written a tool just for demo purposes, and I've called it MySQL Sniff. It's not going to always work. It's just an idea of how you could approach this kind of thing. The way MySQL Sniff works is it attaches to a Java process, and it tries to look at all the socket calls it makes and identify MySQL protocol packets, parse them, and then display the query that was being executed. And in this example, I've also added a filter. So I'm only interested in this specific query. Now, the filtering is happening in the kernel on the BPF program side. The packet parsing is happening in the kernel on the BPF program side. So there's no files, no logs being generated for every single thing the application is doing. And the output would be something like this. So whenever that particular statement is executed, we would get a print message with the stack trace, where this query came from. And so you're seeing lots of code from the JDBC driver for MySQL, followed by my actual application code, which is responsible for that query. So again, complete full visibility into what the application was doing. It was a bit more effort in this example. Actually had to write a custom tool for this, but more or less the same idea. Do the heavy lifting in the kernel on the BPF program side, and don't push data into files. So that's a few scenarios where hopefully you start to see this as a useful technology. I have a couple more that I want to show you, so let's just go through them quickly. We have 8 minutes, so let's see what we have time for. One thing that could be interesting, and I've already talked about it briefly, is you have a Java app with lots of garbage collections, and you want to figure out where they are coming from. Specifically, you want to figure out where the garbage is coming from. Like, what is allocating lots of garbage? Because that's why garbage collections happen, because you allocate lots of garbage eventually. Or you call the GC yourself, but we've already taken care of that. So here's a Java application that's running and consuming lots of CPU, as we have already seen before. And here, I've also run a tool called ustat from BCC, BPF-based, which prints the number of garbage collections per second executed by each process it traces. So here you see for that Java process, I'm showing like 800, almost 900 garbage collections per second. And that's, again, a bit suspicious. I would want to bring this probably down. So I want to understand where they are coming from. Now, if I just run a general profiling tool on this app, like the profile tool that we were already talking about before, it shows, there's a bunch of different things happening, but one of the stacks responsible for actually lots of CPU usage is this stack here, which is allocating new arrays. So even before we can trace allocations, which I'm going to do next, we can already see that a lot of CPU time in this process is just from allocating new arrays, new Java arrays. But we can do better than that. We have a tool in BCC for tracing allocations, for tracing which kinds of allocations an application is doing. So that's called uobjnew. And it's a tool that, again, it supports other languages as well. The reason it's not a Java-specific tool, it works for other languages as well, is that other languages have trace points also, and other languages have trace points for object allocations, among other things. So this is a tool that actually works with Ruby as well, for example, not just Java. In any case, it tells me that these are my top allocated types: strings and open bracket C, which is array of characters. So strings and arrays of characters are the things I am most frequently allocating. And this is already interesting. It could lead to the potential source of where this is happening. But I could do even better. I could figure out, again, the call stacks or a flame graph of where these allocations are coming from. So not just which types are allocated, but where in my code am I allocating these types. And that would require another tool, which is very similar to the profile tool. And this is a tool called stack count. Stack count is a tool that you point at a certain event, and it will tell you which stack traces lead to that event often. So it's like CPU profiling, but not just for CPU profiling, but for anything. For object allocations, for file writes, for network accesses, for whatever you want, you can do kind of profiling and get the stack traces for that event. And in this case, we are using stack count with the JVM object allocation event. And the result we get is stack traces of where heavy allocations are happening in that Java process. And you see the stack trace here leads to the same new array Java call stack that we've already seen before. And the number of events here was 870. So again, stack count just counts the distinct call stacks leading up to a particular event, in this case, to object allocations. So this was a slightly more complicated demo, and we've seen a bunch of different things. But the key ones for object allocation scenarios were uobjnew and stack count, which helped us identify where the heavy allocations are coming from. So I think I have time for just one more. And let's take a look at this one as well. So in this example, we have this Java process which fails to initialize and prints these weird messages suggesting something is missing. Here's what it looks like. So error opening, sorry, not error. Server started initializing, and then opening config file, opening config file, opening config file, opening config file. You might suspect at this point something's wrong with that config file. And so, again, we have a methodical approach for this. We don't have to randomly search the code base for where this message could possibly be printed. If we think the application is failing to open a file, then we have a tool, a BPF-based tool from BCC called opensnoop, which will trace failed file opens across the system. And so if you run opensnoop-x, x for failures, it will tell you that the Java process is constantly trying to open a non-existing file here, etc acme svr config. And the reason I say it doesn't exist is that we can see the file descriptor being returned, -1, and the error is 2, and error 2 is file not found. So that file doesn't exist. And I could do one better. I could tell you where the application is trying to open that file. Because again, remember, for any event, we could also get the stack trace. So here's the trace invocation for this. Trace the Java process, print me a user space call stack, and look at the sysopen function in the kernel, which is the implementation of the open system call, but only when the return value is -2, and then print the message failed open. And the way it looks like is we get that message printed, but more importantly, we get the stack trace inside the Java application, which was responsible for that failed open. And by the way, these arrows you see here, this is inline functions. So even those could be traced if we have the right information in our perf map. OK, so that's my final example, I think. I'll wrap up at this point. There's a couple more if you'd like to take a look at the slides. It's really quite useful for tracing the internals of the JVM, things like garbage collections and allocations, but also system-level events which just happen to be happening in your Java process, like file writes, network events, disk accesses, and so on. So I'm going to skip the last one and just wrap up. I wanted to show you how BPF can really change the world of Linux tracing tools by creating tools that work in real time, aggregate information, and print it out immediately. They don't force you to go through expensive files and post-processing these files later. We've seen a bunch of useful tools that work with JVM applications, and there's a lot more. I could show you 10 more scenarios like this if we had a bit more time. And I've shown you also some examples of where we're not really running like this one specific tool for one specific problem. I've shown you a couple of examples of stack count, trace, and argdist. And these are general tools. Once you master the syntax, you can use them for a lot of different kinds of investigations. You can write one-liners that trace different interesting things around the system. There's some references here. If you're interested more in BPF itself, or in BCC, there's a bunch of really good tutorials by Brendan Gregg on the BCC GitHub repository. And you can find the slides here, and the demos I've been showing you are all up on GitHub. And there's a bunch of additional exercises that you could work through if you want to practice these things as well. I'm out of time, so I'm going to step down. And if you have any questions, please catch me outside if you'd like, or during the breaks. Thank you very, very much.